In this lecture, we are going to discuss how to solve a differential equation in power series about some singular point about x is equal to 0. So at first assume that d square y by dx square plus p into dy by dx plus q into y is equal to 0. This is a differential equation where p and q are polynomials in x. So this is the standard format of the differential equation, and we are going to solve this differential equation in series solution method or power series method when x is equal to 0 is a singular point. So if x minus 0 into p and x minus 0 whole square into q are not infinite at x is equal to 0, then we will say that x is equal to 0 is a regular singular point. Otherwise, it is an irregular singular point. It means that there may be two types of singular point: regular singular point and irregular singular point. So, how to identify that they are regular or not? We have to calculate these values. Suppose x is equal to 0. We are calculating the solution about the point x is equal to 0. In that case, you have to calculate these two factors. The first factor is x minus 0 into p, and the second factor is x minus 0 whole square into q. So if they are not infinite at x is equal to 0, then x is equal to 0 is a regular singular point. So at first we will take some examples for regular singular points or irregular singular points. So let us assume that this is a differential equation. For example, 2x square d square y by dx square plus 3x into dy by dx plus x square minus 4 into y is equal to 0. So whenever we are given some differential equation to solve in series solution method, so firstly we have to convert this differential equation in the standard format. Standard format means in this format, that is d square y by dx square plus p into dy by dx plus q into y is equal to 0. This is the standard format. So after expressing the differential equation in standard format, we will obtain, that is d square y by dx square plus c by 2x into dy by dx plus x square minus 4 by 2x square into y is equal to 0. This is the standard format of the given differential equation. So the value of p is 3 by 2x and value of q is x square minus 4 divided by 2x square. So this is p and this is q. Now it is clearly seen that if we put x is equal to 0, you see that if we put x is equal to 0, then p will become infinite. So clearly x is equal to 0 is not ordinary point. But if we calculate x minus 0 into p and x minus 0 whole square into q, then you will see that in that case this first factor, that is x minus 0 into p, that will become 3 by 2. So it is not infinite at the point x is equal to 0. And this factor, that is x minus 0 whole square into q, that will become ultimately half into x square minus 4, and again it is not infinite at the point x is equal to 0. So x is equal to 0 is a regular singular point. Let us take another example. Suppose this is a differential equation. So after expressing the differential equation in the standard format, you can calculate the values of p and q. So here p is equal to 2 by x minus 2 and q is equal to x plus 3 by x into x minus 2 whole square. This is the expression for p and q. Now p and q are not analytic. That means p equal to infinity and q equal to infinity at the point x is equal to 0 and x is equal to 2. It is clearly seen. You see that in the denominator there is x. So if we put x is equal to 0, then p will become infinite, and not only 0, but again if you put x is equal to 2, then again p will be infinite. So x is equal to 0 or x is equal to 2, they are not ordinary points, rather they are singular points. Now you have to check that whether they are regular singular point or irregular singular point. Then you have to calculate those factors such as x into p and x minus 0 whole square into q. For the point x is equal to 0, you see that there are 2 points actually, x is equal to 0 and x is equal to 2. So let us calculate x is equal to 0 at first. So x minus 0 into p, that will become 2 by x minus 2, and it is not infinite at the point x is equal to 0. And if we calculate x minus 0 whole square into q, just like previous example, so you will obtain this factor, and if we put x is equal to 0 here, then it will not become infinite at the point x is equal to 0. So as x into p and x square into q are not infinite at the point x is equal to 0, so x is equal to 0 is a regular singular point. Now let us check the example for x is equal to 2. So again you have to calculate x minus 2 into p. Just we have in the previous example we have calculated x minus 0 into p. So you have to calculate x minus 2 into p for the point x is equal to 2. So x minus 2 into p, that will become 2 by x. So that is not infinite at x is equal to 2. And x minus 2 whole square into q, and that is become x plus 3 by x. So again it is not infinite at the point x is equal to 2. So for the point x is equal to 2, x minus 2 into p and x minus 2 whole square into q, and they are not infinite, so x is equal to 2 is a regular singular point. So for the regular singular point, if x is equal to something, it may be 0, it may be 1, maybe 2, whatever it is, if the point is regular singular point, then we will apply a special method for the series solution. The name of the method is Frobenius method. So we are assuming that x is equal to 0 is a regular singularity of the given equation, and this is the standard format of the given equation. So if x is equal to 0 is a regular singular point of the equation, then the series solution of the given differential equation can be written as y is equal to x to the power m in the first bracket a0 plus a1x plus a2x square plus a3x2 plus so on. That means ultimately we can express y is equal to k equal to 0 to infinity ak x to the power m plus k. This is the solution of the given differential equation. And if y is this one, then what we have to calculate, that is y dy by dx d square y by dx square step by step. And from the equation, you have to calculate the value of m. You see there is a value of m here. So you have to calculate the value of m, and on calculating the value of m, there may be different types of solution that we will step by step show here. So suppose in the case 1, we are assuming that is the roots which we have obtained, uh, that is m1, m2 are distinct and they do not differ by an integer. So suppose m1 is equal to half and m2 is equal to 2, then the complete solution will be y is equal to c1 and y for m1 plus c2 and y for m2. So in this lecture, we will confine in this case only, that is in the case 1. And now I am going to describe uh, some examples. So from these examples, it will be clear that is how to solve the differential equation in series solution method or the Frobenius method. So let us take some examples. So I have already told that in this case, we are going to discuss the first case, that is when the roots are distinct and not differing by an integer. So this is the expression of the differential equation 3x d square y by dx square plus 2 into dy by dx plus y is equal to 0. And this is the expression of the differential equation. And we are going to find the solution of the differential equation about the point x is equal to 0. So at first you have to verify, that is whether x is equal to 0 is a regular singular point or not. You have to at first verify it. That is whether it is ordinary point or singular point. If it is singular, then whether it is regular singular or irregular singular. But kindly note that we are only going to discuss the regular singular points here, but still you have to check whether it is regular singular or not by uh, taking the values of x into p and x square into q. So you will see that if you check it, then you will see that x is equal to 0 is a regular singular point. So in the first step, we have to assume that y is equal to ak into x to the power m plus k. This is the solution of the given differential equation. So dy by dx will be ak m plus k x to the power m plus k minus 1, and d square y by dx square will be ak m plus k minus 1 x to the power m plus k minus 2. So this is the values of dy by dx and d square y by dx square. Next we have to substitute the values of y dy by dx and d square y by dx square in the given differential equation. So after the substitution, the equation becomes like this. So you have to simplify it, because you see here there is a power of x to the power m plus k minus 1. This is also x to the power m plus k minus 1. Then you have to take it common. So this is the coefficient for the x to the power m plus k minus 1, and this is x to the power m plus k. Ak is the coefficient for the x to the power m plus k. So after simplification, we are obtaining this equation in summation format. Now, what you have to do? At first, you have to make the coefficient of the lowest degree term. The coefficient of the lowest degree term x to the power m minus 1 in the identity is obtained by putting k is equal to 0 in the first summation only and equating it to 0. That means your target is that coefficient of the lowest degree term of x, that coefficient you have to make it 0. So how to do that? You see, that is what is the power of x here, m plus k minus 1. And what is the range of k? Range of k is 0 to infinity. So at first you assume the lowest value of k, so k is 0. Then this will become x to the power m minus 1. And if we put k is equal to 0 here, then it will be x to the power m. So what is the lowest degree of x? That will be x to the power m minus 1 naturally, because lowest value of k is 0. So the lowest power of x is x to the power m minus 1. So that you have to make the coefficient of the lowest power of x to 0. So for that purpose, what you have to do, you have to uh, put the value of k 0 here, and this coefficient, you have to make this coefficient to 0, because this is x to the power m. So we are going to do nothing here. Only this coefficient you have to make it 0 after putting k is equal to 0. So that we have done here, that is a0 3 into m minus 1 plus 2m is equal to 0. So therefrom we are obtaining an equation involving m. The name of this equation is known as indicial equation. This is the important step for the Frobenius method, because depending on the step, there are different types of case, uh, and for the different types of cases, different types of solutions are obtained. So these equations, when you will calculate the coefficient for the lowest degree term x to the power m minus 1 and make it 0, so from that step, you will obtain a special equation that is known as initial equation. So from the initial equation, you will obtain the values of m. You see the values of m are 0 and 1 by 3, and they are different, distinct, and they differ not by an integer. You see the heading of the case 1, that is when the roots are distinct and not differing by an integer. So here the roots of m, or the roots of the initial equation, are different, 0 and 1 by 3, and they are not differing by an integer. The difference is 1 by 3, so it is not an integer. So this is the case 1 that we are going to discuss in the first lecture. So as m is equal to 0 and 1 by 3, so they are different, and and they are not separated by an integer. So next we will calculate the coefficient of next lowest degree term x to the power m in the identity 2. After this process, in this process we have calculated the coefficient of the lowest degree term x to the power m minus 1. In the next step, At first, we will calculate the coefficient for the lowest degree term x to the power m, that is the next lowest degree. And how to calculate the coefficient for x to the power m? So for that purpose, we will put k is equal to 1 in the first term, because you see, if we put k is equal to 1 here, so the power will be m plus 1 minus 1, means x to the power m. So then we can calculate the coefficient for the x to the power m. So if we put k is equal to 1 in the first term, then we can calculate the coefficient of x to the power m. And in the next term, that is in the second term, if we want to calculate the coefficient for the x to the power m, then we have to put k is equal to 0. So after putting k is equal to 1 in the first summation and k equal to 0 in the second summation and equating it to 0, we will obtain this equation. And from this equation, we will obtain a relation between a1 and a0. Third step is to calculate the coefficient of x to the power m plus k, and we have to equate the coefficient of m plus k to 0. So this is the equation. So how to calculate the coefficient of x to the power m plus k? If we want to calculate the coefficient of x to the power m plus k, then for the first term, if we want to make it m plus k, then what we have to do? We have to put k plus 1 in place of k, then it will be m plus k. So in the first summation, we will put k plus 1 in place of k, and the second term is we have to do nothing, because it is already x to the power m plus k. So uh, in the first term, you see, that is, we have written k plus 1 in place of k. That was ak, but we have written ak plus 1. That was m plus k, but we are writing m plus k plus 1, and so on. And for the second term, it is already x to the power m plus k, so we will write ak only, and we have to make this expression 0. So therefore, we will obtain a generalized expression for the a. So this is the generalized expression, ak plus 1 is equal to this one. This is also known as the uh, generalized equation or the recurrence relation. So from the recurrence relation, we can calculate different values of a. For example, if we put k is equal to 0, then we will obtain a1. For k equal to 1, we will obtain a2. For k equal to 2, we will obtain a3, and so on. Now, after calculation of these terms, what we have to do, you have already seen that there are two different values of m. The first value is 0 and the second value is 1 by 3. So for the first case, that is for m is equal to 0, you have to calculate these values. You have to put the value of m 0 here. Then we will obtain a1, a2, a3, so on. So these are all for m is equal to 0. So for m is equal to 0, the equation will be y1 is equal to a0. You see again the equation, standard equation, y is equal to sum of ak x to the power m plus k, means a0 x to the power m plus a1 x to the power m plus 1, and so on. So from that general equation, y1, that is first solution, will be this one for m is equal to 0. But there is another value of m, that is m is equal to 1 by 3. Then again, what you have to do, you have to calculate a1, a2, a3 by substituting the value of m is equal to 1 by 3. Then again, you will obtain this coefficient. And for this coefficient, there will be second solution. So second solution will be again y2 is equal to. So you have to put these values in the standard equation for standard power series. Then you will obtain the second solution. So the complete solution will be y is equal to a into y1 plus b into y2, where y1 is equal to this one and y2 is equal to this one. So y is equal to a into y1 plus b into y2 is the complete solution. So let us take another example. Suppose this is the equation. Again, we have to test that whether the point x is equal to 0 is regular singular or not. This is the first step. After checking that it is a regular singular point, then we have to assume that y is equal to sum of ak x to the power m plus k is a solution of the given differential equation. Then calculate y prime, then calculate y double prime. Next, we have to substitute these values in the given differential equation. So after substitution, you are obtaining this equation. Then you have to simplify a little bit. So after simplification means actually what you have to do, you have to express this equation in different powers of x. So ultimately, after simplification, this is the simplified expression. That is, in the first expression, the power of x is m plus k minus 1, and in the second expression, the power of x is x to the power m plus k. So again, just like previous example, at first we have to calculate the coefficient of the lowest degree term x to the power m minus 1. So you have to put k is equal to 0 here. Then you have to make this coefficient equal to 0. And if we make this coefficient equal to 0, then you will obtain the initial equation, and you will check that from this initial equation the values of m are 0 and 7 by 3. So this is matching the criteria of our case that we are going to discuss in this lecture. So m is equal to 0 and m is equal to 7 by 3. The next step is to calculate the next lowest degree term x to the power m, and you have to make this coefficient equal to 0, and from that equation again we will obtain a relation between a1 and a0. The next step is to calculate the coefficient of x to the power m plus k and make it 0. So just like previous example, you have to calculate the coefficient of x to the power m plus k. So after calculation, you will get a general equation or the recurrence relation. So this is the recurrence relation: ak plus 1 is equal to 3m plus 3k plus 1 divided by 3m plus 3k plus 3 into ak. This is the recurrence relation. Now we have already seen that there are two values of m. The first is m is equal to 0 and the second is m is equal to 7 by 3. And from the recurrence relation, you have to put m is equal to 0 here. At first you have to put m is equal to 0 and calculate different values of a after putting different values of k, that is k equal to 0, k equal to 1, k is equal to 2, and so on. So you are calculating a1, a2, a3 different values of a by considering m is equal to 0. Similarly, for m is equal to 7 by 3, again from this recurrence relation, after putting m is equal to 7 by 3, you have to step by step calculate a1, a2, a3, so on, by putting k is equal to 0, k is equal to 1, k is equal to 2, and so on. Next, we will obtain two types of solution. That is, for m is equal to 0, and this is the first solution. Y is equal to this one. This is the first solution. And for m is equal to 7 by 3, we will obtain another solution. Y2 is equal to this one. So these two solutions are linearly independent, and the complete solution will be y is equal to a into y1 plus b into y2. So in this way, we can calculate the differential equation for the particular case when the roots of the initial equation are distinct and they are not differing by an integer. There are some another cases also, and we will discuss those cases in separate lectures. And I request you to check more examples from the book of H.K. Das and Bharma. The name of the book is Higher Engineering Mathematics. And I thank you all for listening this lecture.